Uh, Dear students, today I am going to start uh, the topic linear programming problem with code MSC 455. So this is the syllabus of this subject. I will send it to you on the Google Classroom. Okay. So the first unit is basically the introduction to LPP. Here we will discuss graphical method, simplex method, big M method, two-phase method, dual simplex method, etc. In the second unit, we will discuss assignment problem and transportation problem and then job sequencing. In the third unit, we will discuss game theory, broadly game theory. Then in the fourth unit, we will discuss about the replacement problems. In the fifth unit, we will discuss inventory and queuing theory. In the sixth unit, we will discuss the CPM and PERT, project management techniques, PERT and CPM. Okay, so this is the broad idea of the subject, and as far as the books are concerned, we will follow H.A. Taha, Operations Research and Introduction. This is the third edition. Macmillan Company is the publisher. Okay, and in our library we are having enough number of books. This book can also be found on Google. You can find out it. Second very good book is the Hiller and Lieberman, and the title is Introduction to Operations Research. Publication is McGraw-Hill. Okay, and another very good book is G. Hadley. This is Linear Programming, Narosa publication. And last book is this Kanti Swarup, P.K. Gupta and Manmohan. This is Indian author book, and obviously this is another very good book. And the title is Operations Research. In our library, we can also have this book. Okay, so this is the broad overview of the syllabus. So today we will start this introduction to linear programming problem. So first, what is linear programming problem? Obviously, in a linear programming problem, basically what we will have constraints and objective functions. So let's see. So in a linear programming problem, in a linear programming problem, in short LPP, basically we have three important you can say the ingredients. One is the objective function, second is the constraints, and the third is the basically the we can say we have non-negativity conditions. And to define all these three, objective function, constraint and non-negativity, we need decision variables. So we need decision variables. Okay, now objective function, this is linear. Constraint, these are sorry, these are also linear. Okay, so this is the linear programming problem. If either objective function or constraint, if any one of them are not linear, that means they are non-linear, then the programming problem is known as non-linear programming problem. Fine. So today our task is to define or to establish a linear programming problem. So first we will establish the linear programming problem. Then to solve, so what is our task? Our task is basically first the mathematical formulation. This is our task, mathematical formulation of LPP. This is our task. Once we formulated a linear programming problem, then its solution. Now depending upon the methods. For example, if we have problem of 2-dimension, 2D problem, then we can apply graphical method. But if our problem is 2D, 3D and so on, higher dimension, then we can use simplex method. Okay, or we can use begin method, or we can use dual simplex method, or we can use two-phase method. Okay, and all these methods have their limitations. Or they can apply on certain type of linear programming problems. Fine. So we will see later on, but today our task is the mathematical formulation and graphical method. This is our task. Okay, so let's see. So first is the mathematical formulation of the problem. So this mathematical formulation is divided into 5 steps. Step number 1, study the given situation to find the key decisions to be made. Okay, first we will study the situation. Then step number 2, identify the variables, that means decision variables involved, and designate them by symbols like xi, where I is 1, 2, 3 and so on. In step number 3, state the feasible alternatives, which generally xi is greater than equal to 0 for all I. These are the general conditions and also known as non-negativity conditions or feasibility conditions. Okay. Step number 4, identify the constraints in the problem and express them as a linear inequalities or equalities. These are also known as the constraints. Okay. Step number 5, identify the objective function and express it as a linear function of the decision variables. So these are the 5 broad steps. Let's see a very famous problem, the ready mix company problem, and this problem is basically a maximization model. Here we have to maximize our objective function. Let's see the problem. Ready mix produces both interior and exterior paints from 2 raw materials denoted by M1 and M2. The following table provides the basic data of the problem. Okay, this is the raw material M1, raw material M2, and because using these two in a different ratio, ready mix basically provides the exterior and interior paints depending upon their ratio, and the data is given herein. This is the exterior paint, this is the interior paint. Okay, and this data is given in tons of raw material per ton of the exterior paint and interior paint. So if ready mix wants to produce exterior paint, then they basically use the ratio 6 and 1. 6, for example, 6% of raw material M1 and 1% raw material M2. In this ratio, they can produce a 1 ton of basically the exterior paint. And the profit for exterior paint per ton is 5 into $1,000. So this is the profit on per ton, 5 into $1,000. That means $5,000 is the profit on each ton if they are producing exterior paint. Similarly, for the interior paint, the ratio is 4:2. 4% raw material M1 and 2% raw material M2. And the profit on each ton of interior paint is 4 into 1000. That means $4,000 per ton. Now, the maximum availability of raw material M1 is 24 tons daily. This is the daily availability. And the raw material M2 is available only 6 tons in a day. Okay, this is the constraint. Fine. And this problem is taken from H.A. Taha book. Hamedi Taha book से मैंने book से ये problem लिया है. This is a very famous problem. Okay. Now, a market survey indicates that the daily demand for interior paint cannot exceed that for exterior paint by more than 1 ton. Okay, a market survey indicates that the daily demand for interior paint cannot exceed that for exterior paint by more than 1 ton. Also, the maximum daily demand for interior paint is 2 tons. This is another constraint. Third one, Reddy Mix wants to determine the optimum best product mix of interior and exterior paint and maximize the total daily profit. This is the task. Okay. So now we will formulate this problem mathematically. So let's see. The variable of the models are obviously the quantity of interior and exterior paints. Suppose x1 is equal to nothing but the tons produced daily for exterior paint, and x2 is the tons produced daily of interior paints. This is the daily production of exterior and interior paints. So what will be the total profit? Total profit can be evaluated with the help of this data table. If x1 amount of exterior paint is produced daily, then obviously profit will be 5 into x1 into 1000. So we are not using 1000, we just generally use this 5 into x1 amount. This will be the total profit on exterior paint. Similarly, x2 is the quantity produced daily on interior paints, and 4 is the total profit. So obviously the total profit will be 4 into x2. So the total profit, overall profit will be nothing but maximum of z is equal to 5x1 plus 4x2. This is the total overall profit. This is due to the exterior paint, and this is due to the interior paint. Okay, and this is in dollars, $1,000. Whatever be the value we have, just multiply by 1000, we will have the total profit. Fine. Now the constraint. The raw material restrictions are expressed verbally, because if you will see the table, then 24 tons will be available for material M1, and M2 material will be available only 6 tons. So obviously x1 is the amount. So if x1 is the amount of exterior paint, and exterior paint is basically you can say produced by using this ratio. Similarly, x2 amount of interior paint is produced with this ratio. Then obviously M1 is used 6 into x1 plus 4 into x2, and this total amount of M1 should be less than 24, because this is the total daily availability. Similarly, 1x1 plus 2x2 should be less than 6 unit. This is the total availability of M2 material, and hence we can say that we have this raw material of M1 is 6x1 plus 4x2 is less than 24, and x1 plus 2x2 is less than equal to 6. This is the raw material of M2. Fine. Now, third restriction is due to this. A market survey indicates that the daily demand for interior paint cannot exceed that for exterior paint by more than one. That means the difference between the interior paint and exterior paint should be less than equal to 1 ton, and hence this is x2 minus x1 should be less than equal to 1. This is market limit. Another constraint is also given to you. Also, the maximum daily demand for interior paint is 2 tons. That means x2 should be less than equal to 2 ton. So x2 should be less than equal to 2 ton. This is the maximum daily demand. So these are the 4 constraints. These are already given to you. So this is our objective function. These 4 are our constraint. And now the non-negativity condition should be x1 should be greater than equal to 0 and x2 should be greater than equal to 0. So ultimately the problem is this. This is our objective function 5x1 plus 4x2 subjected to these 4 constraints. This is for the raw material M1, this is for the raw material M2, and this is the basically the market survey, and this is for the daily demand, and this is the non-negativity condition. So these are basically this is our linear programming problem. Okay, fine. So now here is a note. Any value of x1 and x2 that satisfy all 5 constraints constitute a feasible solution. So feasible solution is nothing but if any solution which satisfy these 5 conditions is known as the feasible solution. Otherwise the solution is infeasible. Okay, for example, x1 is 3 ton per day, x2 is 1 ton per day. When you put it in all these constraints, then they will satisfy 1 to 5 all the constraints and the solution is feasible. However, if you take x1 is 4, x2 is 1, then this is infeasible because this will not satisfy the constraint number 1, because 4x1 means 24 plus 1x2 means 4. So 24 plus 4 is 28, but 28 is not less than equal to 24. So that's why this is infeasible. Okay. So now what is our goal? Our goal is to find a solution, optimum solution, which basically satisfies all the 5 constraints and at the same time maximize the objective function. This is our task and known as the optimum solution. Fine. So now similarly we have another problem which is the diet problem, and this is a minimization model. So the objective of a diet problem is to ascertain the quantities of certain foods that should be eaten to meet certain nutritional requirement at a minimum cost. Basically we want to eat a food which have maximum nutritional requirement, but at the same time we have to pay minimum amount. Okay, so the consideration is limited to milk, beef and eggs and to vitamins A, B, C. This is our basically the consideration. We are considering only milk, beef and eggs and vitamins A, B and C. The number of milligrams of each of these vitamins contained within a unit of each food is given below. So this is the table. Here we have vitamin A, B and C. Then we have discussed the milk. In a gallon of milk, how much we have vitamin A, vitamin B, vitamin C, and what is the cost. Similarly, per pound of beef, how much we have A, B and C, and the cost. Similarly, dozens of eggs have how much amount of A, B and C, and the cost of dozens of eggs this is given to you. Okay, and this is the minimum daily requirement. Fine. So here for milk we have in a gallon of milk, basically vitamin A presents in a unit. This is in the unit, 1 unit, B 100 units, and C is the 10 units, and the cost is rupees say 1. This may be in rupees, this may be in dollars, or maybe any unit. Similarly, pound of beef contains 1 unit of vitamin A, 10 units of vitamin B, and 100 units of vitamin C, and the cost is rupees 1.10. Similarly, dozens of eggs have 10 units of vitamin A, 10 units of vitamin B, and 10 units of vitamin C, and the cost is rupees 0.50. Now the daily minimum requirement is 1 milligram of vitamin A, 50 milligram of vitamin B, and 10 milligram of vitamin C. Now what is the linear programming formulation for this problem? Our task is to basically invest minimum cost and consume maximum nutritional requirements of our daily need. Okay, so let the daily diet be consist of x1 gallons of milk, x2 amount of pounds of beef, and x3 dozens of eggs. This is our daily demand. Now based on this data, the total cost per day will be obviously rupees 1 into x1 amount we have to invest on milk. Similarly, x2 into 1.10, this cost we have to invest on beef, and 0.50 into x3, this amount we have to invest on eggs. So the total cost will be x1 into 1, so x1, plus x2 into this, so 1.10 x2, plus x3 into 0.50, this is the eggs. So this is the total cost. Now as far as the restrictions are concerned, this is the minimum daily requirement. So we have to take more than that, but not less than 1 unit. And that's why how much amount of vitamin A we have to consume? x1 into 1 plus x2 into 1 plus x3 into 10. So x1 plus x2 into 10 x3, and this should be greater than equal to 1 because this is the minimum daily requirement. So greater than equal to 1. Okay, similarly 100 into x1 plus 10 into x2 plus 10 into x3, this should be greater than equal to 50 milligram. This is for vitamin B. This is for vitamin A. This is for vitamin A. This is for vitamin B. And this is for vitamin C. 10 into x1, 100 into x2, 10 into x3. This should be greater than equal to 10 milligram. And obviously we have to consume x1, x2, x3 amount of milk, beef, and eggs, and all these three should be greater than equal to 0. This is the feasibility condition. So ultimately what is our problem? Minimize this cost. So this is our cost subjected to this constraint, and this constraint. So they are listed here along with this feasibility condition. So this is our problem. So we have taken a minimization problem, and this minimization problem is of basically a 3-dimensional problem. Here we have x1, x2, and x3. So this is a 3-dimensional problem. However, our previous problem, ready mix problem, this is a 2-dimensional problem because we have only 2 constraints, x1 and x2, and problem is of maximization. Fine. So now, because today our task is to solve a linear programming problem with the help of graphical method, so we will consider only ready mix problem because this is a 2-dimensional problem. We can solve this easily with the help of a graph. Okay, so let's see the graphical way how we can solve the ready mix problem. Now, so the graphical LP solution, LPP solution, linear programming problem solution. Okay, the graphical solution includes 2 steps. First, determination of the feasible solution space, and the second is determination of the optimum solution from among all the points in the solution space. Okay, now to locate the feasible region bounded by any constraint, following figures may be useful. Suppose we have, because every constraint you can see here, we are having of this kind, either less than type, or either, for example, herein we have greater than type. Okay, so that's why this is, for example, y plus mx is equal to, see, this is the line. So if we are having constraint which is y plus mx less than type, then we will cover up this region. Otherwise, if reason problem is y plus mx greater than c type, then we have to take this feasible region. Similarly, if suppose our line is of this form, y plus mx is equals to c type, then if we have this type of problem, y plus mx is less than c, then we have to take this region. And if our problem is of this kind, y plus mx greater than c, then we have to take this region. Okay, so this is the broad overview. Let us see the ready mix problem. So example number 1, this example solves the ready mix problem of example 1. This is the ready mix problem. Maximum z is equal to 5x1 plus 4x2, subjected to 6x1 plus 4x2 is less than equal to 24, x1 plus 2x2 is less than equals to 6, x2 minus x1 is less than equal to 1, and x2 is less than equal to 2. And these are to the feasibility conditions. x1 is greater than equal to 0 and x2 is greater than equal to 0. So these are total, basically we have 6 constraints. Okay, so now first we will draw these lines based on this. So here, for example, first if you draw this, so what you do, just take x2 equal to 0. When you take x2 is equals to 0, then what will be the x1? X1 will be nothing but 24 divided by 6, so that means 4. So this will be the 4 here, 4. Okay, similarly in the first, let's see, first we will write down this and then we will discuss this. First we will write down, otherwise this will create a problem for me. So this is the maximum. Let's see, we have basically, yes, we have this same thing we have written here. So let's see how we can model this. Okay, so this is, so here first we put x2 is equal to, so this is x2 axis, this is our x1 axis. Okay, so now first we will draw the constraint number 1. So put x2 is equal to 0, so we get x1 is equal to 24 divided by 6, so 4. So let's see, this is the point. Then put x1 is equal to 0, then we will get x2 is equal to here 6, x2 is equal to 6, so this is the 6. Now join these two lines, 2 points, and this, since this is the first constraint, so denoted by this 1, encircled was 1, and since this is less than type, so reason will be like this. This will be the reason, this reason. Okay, second constraint is this, put x2 is equal to 0, so we get 6, so we get this point. Okay, then put x1 is equal to 0 and get x2 will be 3, so this will be the 3. So now join these 2 points and this will be the second constraint. Okay, and the reason will be less than type, this reason. Okay, now the third one, here put x2 is equal to 0, so x1 will be minus x1 is less than equal to 1. Okay, so the point will be somewhere here, this will be the point when x1 is minus 1, because this is 0, this is positive 1, this will be minus 1 here, somewhere we have minus 1 here. Okay, this will be say minus 1. Okay, then put x1 is equal to 0, so x2 will be 1, so this point will be x2 equal to 1. Join these 2 points, so this will be the reason. And since we have this restriction, x2 should be greater than equal to 0, x1 will be greater than equal to 0, 5 and 6, so we have to take only the positive of this axis. So that's why we will consider only this part, we will consider only this part, we will not consider this part, negative part. Okay, now so this is denoted by third constraint. Okay, now the fourth constraint, x2 is less than equal to 2, So this is x2 is equal to 2, and this is this line, basically this line is, so we are having this line, this region is basically the fourth constraint. And 5 and 6 basically they are nothing but the positive axis, so this is the positive axis. Okay, so ultimately the common area will be this, the shaded part will be the common area. And here we have the corner points A, B, C, D, E and F. These are the total 6 corner points. Okay, so this is basically known as the feasible solution space. Okay, so this is basically the, now we have to, first we identify the solution space. Now in the second, determination of the optimum solution. Now here we have not draw the objective function 5x1 plus 4x2. Okay, so now to draw this, let's see, designate some value, a random value, suppose say 20, let's say 20. We have why we have selected 20, because is a common factor, you can see 5 and 4, so that's why we have taken 20, so that we can easily find out the point where this objective function intersects the x1 axis and x2 axis very easily. So when you put x2 is equal to 0, so this will give you 5 divide, just 20 is divided by 4, so we get 4. Similarly, when you put x1 is equal to 0, you can easily find out x2 will be 5. Okay, so suppose you have designated 20 here, then you can see what we will get. We will get some values here. For example, say this, if you designate say any value here in, this is a 21 here, so we will have some value here. This line जो हम draw करेंगे 20 की line, वो यहाँ कहीं पड़ेगी. Okay, so when you put x2 equal to 0, so we will get 24. This will be the 4 here somewhere, and when you put x1 equal to 0, so x2 will be 5 somewhere here, 1 2 3 4 and 5 somewhere here. When you join, so we will get some line here. Okay, and now once you draw this line, for example this, then slowly draw the parallel lines such a way that at a certain time you will see that this line basically intersects a corner point, and when you move further, then you will leave the feasible region. So stop at that moment, and the corner point will give you the solution. Fine. So here you will see that when you draw the parallel lines, you will see that suppose this line is nothing but say z is equal to say any value. For example, say z is equal to 10, z is equal to say 15, z is equal to say 20, and finally you will see that when you draw this line z is equal to 21 here, then this line intersects the corner point C. So this is the increasing direction of z. In this direction z is increasing, and here all the lines are basically the parallel lines. Okay, so this intersect the point C, and C will be the optimum solution. So now C is basically the intersection of basically the line number 1 and line number 2. So just solve 1 and 2 and get the x1 and x2. Okay, so when you solve constraint number 1 and 2, then we will get x1 is equal to 3, x2 is equal to 1.5, and z will be 21 into 1000 से multiply किया, so 21,000, this is in dollars, so this will be the solution. Okay, another way is you just find out the coordinate points of A, B, C, D, E, F, and then because here x1 is 0, x2 is 0, put in objective function and get the value. Similarly at this corner point B, x1 is 4 and x2 is 0, put in the objective function and get the value of z, and so on. And among all these, because the problem is of maximization, find out the maximum value of z, that will give you the solution. So C will be the solution. This is the another alternate approach if you don't want to draw these or parallel lines. Okay, so this alternate procedure is shown herein. So here we have 6 corner points A, B, C, D, E, F, x1 x2 points will be 0 0, 4 0, 3 1.5, 2 2, 1 2 and 0 1, and objective function is this, max z is 5x1 plus 4x2. So we have evaluated the value of z. For example, here x1 x2 both are 0 0, so substitute it here and then find out the z. Z will be 0. Similarly here x1 is 4, x2 is 2 at point B, so find out the value of z. Z will be 20. Similarly for C we get 21, for D we get 18, for E we get 13, and for F we get 4. Among all these 6, 21 is the maximum value, and hence maximum profit is x1 is 3, this, x2 is 1.5, and z will be 21 into $1,000. So this will be the solution. Okay. Similarly, we have a problem for minimization. So solve the following LPP using graphical method. So here the problem is minimize z is equals to minus x1 plus 2x2, subjected to minus x1 plus 3x2 is less than equal to 10, x1 plus x2 is less than equal to 6, x1 minus x2 is less than equal to 2, and x1 is greater than equal to 0 and x2 is greater than equal to 0. So these are the problem constraints. Okay, so first we will draw the constraints. So here in first constraint put x to 0, so x1 will be minus 10. So somewhere we have this point, somewhere here we have minus 10, here कुछ यहाँ पड़ेगा point. Then put x1 0, x2 will be 10 by 3, 3.3. 3.3 will be like this point, this point. So now join these points, so we get the first constraint, this. So this is our first constraint. Okay, and the reason is since less than type, so this will be the reason. This will be the reason, and we have to due to these two 4 and 5 constraint, 4 and 5, so we will consider only the positive axis. Okay, now the second constraint, put x to 0, we get x1 6. Similarly put x1 0, so we get x to 6. So join 6 and 6. So this is our second constraint, and since this is the less than type, so we have to consider this region. Now the third constraint, put x to 0, we get x1 is equal to 2. So x1 is equal to 2 this point, and then put x1 equal to 0, x2 will be minus 2. So minus 2 will be somewhere here. When you join, so we get the third constraint here. So we get third constraint, and the region is less than type, so we are getting this region. So the common area is the shaded part, which is the common area and satisfying all these 5 constraints, 1 2 3 4 5. Okay, and this is known as the basically the feasible region. Now designate some value, for example say 2, and then draw the line. So draw 2 here and designate the, suppose 2. So when it equal to 2, then put x2 is equal to 0, so we get x1 is equal to minus 2 somewhere here. Then put x1 is equal to 0, we get x, this because we are designated this as 2. So put x1 0, so we get x2 is equal to 2 by 2, 1. So this will be 1. So when join these two, so we get z is equal to 2. Similarly, this is the line for z is equal to 4. This is the line for z is equal to 2. And now draw the line, parallel lines. And finally, you will see that at this red line, this red line is basically for z is equal to minus 2. So we can see that this is the minimization problem. So in this direction, z decreases. Here z decreases. So this is the feasible direction. And after at this point, you will see that if you draw further lines, then you will leave the feasible space. So solution of feasible space में आना है, तो this will be the basically the corner point of this feasible region. अब इस corner से आगे आप नहीं जा सकते, otherwise your solution space will be leave out. Okay, so this is the basically the solution point. Here you will see that this point is basically the, you can easily evaluate with the help of third constraint. So just put x2 is equal to 0 in the third constraint, so you will get x1 is equal to 2. So the optimum solution is x1 is equal to 2, x2 is 0, and z will be minus 2. Okay, alternately, just like this method, here we have corner points a, b, c, d and e, 5 corner points. Find out there basically the x1 and x2 values, and then you can easily find out the minimum z. So this is the A, B, C, D, E. We have these two corner points x1, x2. These are the points, and based on their values just find out the z. Z will be 0, -2, 0, 6 and 20 by 3, and among these -2 is the least one, and so solution is x1 is equal to 2 and x2 is equal to 0. This is the solution, and z will be -2. Okay, here we have another problem. Third problem. Here minimum z is equal to 20x1 plus 4x2 subjected to 36x1 plus 6x2 is greater than equal to 108. Second constraint, 3x1 plus 12x2 is greater than equal to 36, and then 20x1 plus 10x2 is greater than equal to 100. And feasibility conditions is we have x1 is greater than equal to 0 and x2 is greater than equal to 0. When you draw these 5 constraints as per the previously discussed examples, then we have basically this shaded area. Okay, so you do yourself, so you will see that we will have this shaded area. This is the solution space. When you compare this problem with another two which we have already discussed, so you will see that here we have unbounded solution space. Unbounded means there is no upper bound. We have the lower boundary, this A, B, C and D. This is the lower boundary of the feasible space, but there is no upper boundary. So this is unbounded solution space. But since the problem is of minimization, so when you draw the objective function, designate some value here, for example say 40, then draw the line. This line is basically, for example here z is equal to 400. If you draw this is equal to 400, then you will get this line. This is for z is equal to 400. And since this is problem of minimization, so draw the parallel lines. So here when you draw this line is z is equal to 280, so decreases. Again draw the parallel line, so this corner point will basically give you the solution. At this corner point z will be 160, and this point C is the solution, optimum solution. Here x1 is 4, x2 is 2 and z is 160. So this is the solution. But at the same time, for example, suppose this problem is minimization is replaced by maximization. अगर इसको मैं maximum कर दूं तो, so we have to increase the solution. Z is equal to 400, then 600, 800. There is no limitation, and hence solution is basically unbounded. So here solution space is unbounded, and we have either bounded solution or unbounded solution. Bounded solution in the case of minimization and unbounded solution in case of maximization for the same problem. Okay, so this is the basically the graphical method. I think you understand. And now in the next video we will discuss some special cases of graphical method. Fine, thank you.